Hi, welcome to the gravitational pump. I guess we're all going to sync now. We have a review from the working group that Chloe is going to present. Remember, this is kind of a work in progress. Our goal is to develop this baseline that eventually we hope to publish. So if you have input, please let us know. If you want to help out, please let us know. After Chloe's finished, I think we have lightning talks. One, two. We have two lightning talks, and then Leonard Guidi will talk about the dark shades of something, of particles. So with that, I'll shut up, and Chloe, talk.
Hi, everyone. Thank you for the introduction. I would like to start by thanking the JETZON community and the organizers for the great job they've done for the workshop, and specifically Adrian, of course. Yeah. Okay. I also take this opportunity to thank all the working group members for their contribution, reactivity, even at the last minute or late at night, and specifically David. So my presentation is the result of all the combined work of everyone. The carbon pump is separated into different pumps. I guess you understand that, such as the migrant pump, the mixing pump, and the gravitational pump. The main goal of my talk today is to show you the outcomes of the working group, which is the gravitational pump. So I think I don't have to remind what is the biological carbon pump, but the main goal here is to focus on the sinking flux from the export inside the mesopelagic zone to the sequestration depths below. So how do we measure the gravitational flux magnitude? There are two types of methods, the direct measurements and the estimations. Regarding the direct ones, traditionally, we are deploying various types of samplers, such as sediment traps, either fixed or drifting, in situ pump or marine snow catcher. The sediment traps allow to obtain direct POX fluxes, whereas large volume filtrations can allow to derive fluxes from radioactivity of, for instance, thorium and polonium. Recently, new direct methods emerged based on optic measurement. They can be based, for instance, on images such as the UVP or beam attenuation like the transmissiometer. They can be deployed from a boat or eventually fixed on gliders or bioargo. However, direct measurements are challenging for some reason, and a common approach is the estimation of the fraction of total primary production that is eventually exported. So historically, it was calculated as a ratio between a new production fueled by nitrate supplied from depths and the sum of new production plus regenerated production supported by the recycling in the aphotic zone. Recently, the deep nitrification rate was evaluated as equivalent to the surface rate, which becomes a new source for the regenerated production, leading to an overestimation of the fluxes. So alternatively, we now use the E ratio, which is derived from ratio between export flux measured by thorium and the primary production. So obviously, to estimate the total magnitude of the biological pump, local measurements need to be extrapolated to the global scale. And the sea surface temperature has been found as a good predictor, as you may see on this figure. On the side of indirect estimations, some models are available, generally coupled with satellite data. These are examples, and as you can see, they are all different. Some are tuned by export efficiency and sea surface temperature, others by NPP and phytoplankton size, or even by oxygen or DOC measurement. The NOWIKI model includes migration and mixing pump as well as the gravitational pump. But for comparison purpose, all the results that I will present here is only the extracted gravitational part. So some database already exists for each method. However, they all focus more or less on one method, and there is still no really single census method that is fully satisfying. So in this working group, we aim to update this database and include and merging all the methods in order to see how they converge and if we can create a more complete image of the biological pump. So I will not start to show you where we are in the working group. I remind that this work is under process and they are not final results yet, but it gives an idea. So one of the things we are committing to in this work is taking into account spatial and seasonal variation. So to do so, we agree on 8 regions. I realize that it's not exactly the same as the other working group, so it may be a communication problem at some point, but we can discuss that. This is the one we used here. On this map, you can see a compilation of around 1,000 points of gravitational flux from sediment trap data. Fluxes from depths are ranging from the depths of fluxes are ranging from 50 to 170 meters, and the fluxes from 0.02 to more than 1,000 milligrams per square meter per day. So it's already a substantial data set, but as you can see, we don't cover all areas, and there is a risk of extrapolating too much if we only use those data to globalize on a large scale. We are planning to add the gravitational flux derived from thorium and polonium. The pink points correspond to all the potential data we can have from thorium. I said potential because these are radioactivity data and these are not converted to fluxes yet. This needs a lot amount of time to do it properly and in a consistent manner. But yeah, as you can see, it will cover major part of the region. If we separate the point per season, you can see that we are missing the South Polar winter and the North Polar winter. This is not surprising as there is no light and so less interest in studying the primary production here. The problem is that satellite data are not the best on this region due to the lack of light and cloud coverage. So there is a way to get the primary production from backscatter satellite, but there are some issues with that, and thus we are missing data here to reconstruct the seasonal history of the biological carbon flux. So as I said, we still need time before presenting detailed data of the entire ocean, but that is why we focused here to present you first results on specific sites. We have PAP and Hermes in the North Atlantic region, BATS and HOTS, respectively, in the Atlantic and Pacific part of the North subtropic region, and PAP-A in the North Pacific. On this graph, you can see a comparison of the monthly time series obtained from 3 models. So these are Lowe's et al. 2011, Siegel et al. 2014, and Hansen et al. 2011 models. They are all globally following same tendency. If we now add some direct measurements of different methods, you can see, such as the polonium, thorium, and sediment trap fluxes, you can see a lot of more variability, which could be linked to the method itself or the fact that these are from discrete measurements. We can also notice here that the models are underestimating blooms. So the model can give order of magnitude or average of the bloom, but cannot account for weekly variabilities in the bloom. On this figure, you can see on the top line the exact same graphs as before with the 3 models, and in the bottom line, you can see the average for the entire corresponding region. Obviously, we have some variabilities to explore, but in general, I have the pleasure to tell you that the sites that we are investigating for a few years now are not too bad to represent the tendency of their respective regions. Now here you can see the map with gravitational fluxes estimation from different models. You can see some difference between models and specifically the NOWIKI, which seems on the high side. The difference could be explained because satellite data used can be tuned from field observation based either on sediment trap data or thorium. whereas the no-wiki fluxes are more tied to the deep ocean biochemistry trends with the oxygen and DOC. So it might be an apples versus oranges comparison, and that shows that there needs to be a linking of satellite-based flux to the deeper ocean biochemistry. Here you have the same map, but showing the export efficiency instead of the fluxes. So the results can be different for the same reason as the slide before, but in addition, we should note that the primary production to make the E ratio are different. The value comes from different algorithms, such as the CBPM or VGPM and CBPM mixed. I will not go into the detail here of this algorithm, but this is note that they are important distinctions to be aware of when we are comparing both. So results are nice, results are promising, and I'll be happy to discuss them with you, but in our opinion, this is not the most important topic to address here. We are facing a multitude of issues doing this work, and with issues, the deeper you dig, and the more you find. But that is why we are here, and we all have fun doing our work, so we should be fine. So yeah, there are several approaches to estimate magnitude of the pump and yielding to a large range of estimates. So we are taking a particular attention to the pros and cons of each method and are trying to list them. I will not go into the detail of each method because it would take forever, but there is some examples, such as, for instance, the sediment trap, which can get a signal in short time, or which is easy to track and recover, but in the same time, it's sensitive to surface current or wind stress. So during our meeting, we've got a lot of debates on export depth. You can see on this graph the depth of the aphotic zone based on different definitions for certain cruises. They are very various, and depending on where you are regarding the curve, this can lead to completely different results from the very same data. So for instance, at PAP, depending the depth, you can have depths from 19 to 200 meters, depending on the definition, and the corresponding flux from 29 to almost 300. So we have to really pay attention to the export depths we choose. We had similar debates about the sequestration depth. It is often assumed that below the mesopelagic zone, carbon is sequestrated for millennia. But as you can see on those plots showing the depth at which 50% of CO2 is sequestrated for either at least 100 years or at least 500 years, this is not homogeneous at all. So which metric should we use? 50%, 90%, and about the time, 500 years, 1,000 years? How to choose is not so clear, so we should be paying attention to that as well. So I called the next session future direction, but it's actually more issues. So another question to address is about time scale and steady states, which is a huge one. So the system is not at the steady state, and for instance, after a bloom, the flux at the surface is decreasing over the time, whereas it's increasing at the base of the aphotic zone as the bloom materials are sinking. Export efficiency, which is the metric used, are calculated from the flux above the depth and not above plus before. So that leads to E ratio that can be more than 100%, which is a bit problematic. To illustrate the problem, we tried to invent a simple simulation of a bloom. So this is an exercise assuming that 10% of the primary production is exported to the aphotic zone after 10 days, and that 50% of the flux at the aphotic zone is exported at aphotic zone plus 100 meters with a sinking speed of 20 meters per day. And yeah, the export efficiency is first really low, as the bloom didn't have the time to sink yet, and is progressively increasing, but this is just because the bloom is decreasing at the same time. So yeah, if you do a percentage, it's become higher. I don't know if it was clear, but here are the real data. So on the left, the flux is decreasing with depth with a classic attenuation curve, and on the right, it's increasing flux with depth after the sink of a bloom, leading to unrealistic high values that are more than 100%. So I don't have any solution, but we really may need a new metric to move on. As I said earlier, or maybe not, there are different sinking pathways, which may be detritus, fecal pellet, and phytoplankton cells. They may have different degradation rates, different sinking speed, carbon content, and different quality. The problem is we have very little information available on their relative contribution and season, and according to Siegel model and NOWIKI models, fecal pellets dominate the flux in most of the region, except in high productive zone, where the phytoplankton there is particle dominate. This critically hinders our understanding of the coupling between surface and deep ocean, and therefore our estimate on the carbon sink magnitude. So a way to get this information can be to use the OTS, which was already presented today by Hervé. So it's a sediment trap with transmissiometer and a gel trap. And here you can see a movie of the particles sinking inside the sediment trap tubes. The advantage are that they are direct flux measurement and that the carbon content must be inferred from light attenuation or images. This is a slide to show that we can recover characterization, including the particle size distribution of particles from traps imaging. And using this method, Durkin et al. 2001 obtained gravitational flux by sinking pathway on size, which is really promising. And I guess this is in that type of direction that we need to go to assess the different sinking pathway. Another topic to keep in mind is the shape of the attenuation curve. The attenuation coefficient B vary across season and location, but we still don't really know what drives the B, and as it connects a multitude of processes, it's hard to assess. So measures are still too easily used without contextualization, even when attenuation curve is not applicable. And using the OTS, Durkin et al. Have even shown that the attenuation can be completely different between sinking pathways. So we really should stay cautious when we are using the B coefficient, and we should avoid fixed value as well. So we are still missing a lot of data to fully understand the gravitational component, and linking imaging from UVP or mixed data, which are both increasingly widely collected, should clearly help. So in theory, for the UVP, the POC fluxes could be estimated from the particle size distribution, carbon content, and sinking speed. However, sinking speed and carbon content are still challenging to obtain from UVP data, and thus, in practice, Guidi et al. Proposed an estimation of the POC fluxes from size, assuming a power law for carbon content and sinking speed. I will not dig too much in this way because I guess Lionel will present some part of this work later. But quickly, walking. They found a global relationship between the estimated and measured gravitational flux, but not working. But yeah, there is no local relationship. So this is clearly a direction to dig here. Recently, for the omic data, Kramer et al. Used 18S data and relative abundance of phytoplankton shared between surface and mesopelagic zone to estimate POC fluxes. So as for the UVP, I will not dig too much here, as Sasha is here to present a poster. So I guess you can just ask her if you have so much question about her work. So yeah, more and more omic data are available, specifically from Tara or Malaspina projects. So linking them with POC fluxes could be a good way to fill some gaps. Before my conclusion, I would like to raise a last issue, which is a bit far from what I have presented, but still important. So sharing our science to the public is a part of our job. And regarding particles, they have been compared to galaxy or marine snow, the snow, sorry, which are magic, and even to Salami by Phil Boyd, which is kind of magic as well. So we are passionate scientists, so it's easy for us to see the beauty in particles. However, we are in competition with other topics that inspire our visual and raise curiosity. So my question is, how do you do to make plankton soup attractive and sexy for the public? This is an attempt to summarize all the challenges that we have to face in the future. So this is all the stuff that I presented. They are all required to understand and predict current and future gravitational flux, and thus the biological carbon pump. I tried to list them all here because I thought that maybe these schemes could be useful for the working groups later to keep in mind. So my take-home message, if you have one thing to remember, is that it's a combined work of 15 people, and we are doing it with our own knowledge of literature and current projects, but they are still, as you saw, many gaps to fill ahead, but nothing is impossible together. So if you have any ideas, data, projects to share, or things that we may forgot, just came to see us and contact us. Thank you.
Thanks. Questions for Chloe?
Hey, nice talk. I was wondering, because you said you will consider thicker pellets, phytoplankton cells, and aggregates, but what about something like, copperpot carcasses or zooplankton carcasses and molds and stuff? So are you considering that separately as well, please?
We should.
Okay.
Right. Other questions? Data set.
Hi, I'm Lily from Brown University. I'm wondering if the Southern Ocean time series might be useful. It's a relatively new mooring. Actually, it's 30 years old, never mind. But that might be useful for looking at filling in some of that, the Southern Hemisphere, at least, a point.
Yeah, I think it can be a really good way to follow a bloom sink and to try to understand the problem with the steady state. So we should definitely use time series, and so the sites such as hot baths, we should definitely continue to do it more.
Chloe, you showed some data from Chris Marsay's work, the 4 B values. I mean, given that Chris had 5 different oceanic provinces in his station, and to quote Dave Siegel, you get 2 data points for $50 million US. So, that's quite a little bit of money. But again, the problem we have is in terms of just doing statistics. So I recall in Chris's paper, he sort of drove a line through between the northern latitudes and the low latitude, the southern latitudes was not really anything in the mid latitudes, and sort of said it was temperature. But he's that's sort of playing around with $150 million worth of data. And so, do you think there's a prospect for some of the stuff that Hervé showed, with megastat as optical traps and things like that, to really beat this sort of statistical rap where we're always just poor numbers wise?
I'm not sure. I mean, this is a complex question, the B coefficient. So, yeah, I'm not sure how to answer this. I don't know if someone in the room wants.
Can I just give a quick stab?
Sure,
I mean, in some sense, we don't have an observational proof of what that transmission is. There's models that give different results than what Chris Marseille found out. I think it, you know, it's, I don't know if it's a resolved issue. It is an important one that I know that we need to spend some more time with in the group, that's for sure. Other issues, Deb? Oh, I'm sorry, Jamie.
Yes, Claire, I was wondering if, Debbie Steinberg, Virginia Instrument Science, I was wondering if already your working group is, has some recommendations for future measurements. Like, for example, if you're going to have a field program, you should always have a trap or take a thorium measurement, you know, at the base of the euphotic zone and at 1,000 meter or whatever it might be. Are there some things that you've already seen from going through the data so far that you say, oh, I wish that study had done this?
So the first things, I guess, is to intercalibrate the methods and understand how much they differ and how much basis they can have. We will try to quantify, because between the methods, it's really different, the ranges. So I guess the first things before interpreting the data is to understand, for each of them, how much imperfect they are, if I can say that. So yeah, if there are some cruises which do the really same, which calculate the really same fluxes on the same moment point, and so we can try to understand the difference between. Would be a good first step, I guess.
Oh, I used to work in tech as well. I was just going to ask a bit more of a technical question. I think you showed at the end you had the E ratios as a function of time, and at the beginning you had the satellite estimates. They were seasonal. You had the seasonal. Is that at the beginning? You had the export as a function of.
You mean which slide do you mean?
Oh, it's quite.
Yeah, it's far away, no? Fine. Somewhere. You saw it or not?
At the front, sorry.
That's fake.
Yeah. Oh, okay. Yeah, so I guess the question at the beginning.
That's a concept, yeah.
At the beginning you had like an annual, the trend into annual trend of like, and I think it was from MPP, and you use the E ratios to get at the.
All we did is make a set of rules and make up an NPP and just applied it and calculated what an E ratio and what the TZ ratio would be with those rules.
Yeah. Okay. Yeah. No, that's fine.
That's
I was just interested in that question of, can you apply an E ratio that's been calibrated, or like a global annual scale? Can you apply that to seasonal scale?
You mean one value for everywhere?
Yeah.
I don't like that, but
the point here is that calculating metrics like E ratios and TZ, but that on field data that's unsteady in its nature will give you, different values that don't follow the rules that nature does. Because the NPP here becomes the export here in a couple days. That becomes the transport many days. It was just, working on the unsteady thing. I think we did this on Saturday.
Yeah.
Other questions? Criticisms? Yeah.
Hey, I'm Mara Freilich from Brown University. To the various estimates that have various different spatial distributions of the E ratio, and I was wondering if there's anything that we can learn from the differences between those about, how these spatial, if there's anything we can learn from the spatial distributions about what the various uncertainties and drivers of the flux might be.
Not sure.
Yes, that's my fault. You know, part of it is the different models that were used are calibrated to, so Stephanie's model was calibrated to a global summary of thorium data. The law's data was calibrated to a set of F ratio values from experiments. I'm not even sure what depth it was at, and Ed has not told me what depth they were from. Daniel Clement's recent one is tuned to a global sediment trap and thorium data set, right? Mine is to Boyden. So those are all calibrated to or tuned to observational data. The Nowicki one is tuned not to any of that. It's tuned to what it represents, what the oxygen and DOC distributions and all the, you know, the deep sediment traps, all that stuff has to be. So there might be some apples and oranges there about how they're all created, and you know, I think we obviously have to do a better job to get those reconciled. Did I answer the question as effectively?
Ken Bissler with Woods Hole. Yeah, that was a great tour through the biological gravitational sinking flux. And I was thinking of, you know, you had a quote up there from Andy McDonald, and he showed that, you know, not all the big things sink faster. And so maybe just you could say a bit more about how we're going to take optical methods that require a sinking rate, usually just one sinking rate for a given size class, and get that information to apply to the stocks, because stocks are not the same as sinking. And this type of model shows you, too, that those stocks will be changing. So, yeah, what's your current thought on sinking rate, our ability to measure that, and how important that will be if we're going to be getting fluxes from stocks?
I know that sinking speed is hard to assess from UVP data, so it's hard to use in this, like, with the same data as the one to assess like particle size distribution and stuff like that. So we should. I have no solution yet. Maybe Lionel in his talk after, I don't know, but it's definitely something that we have to improve, sinking speed from imaging. I don't know if I answer.
Any other questions? Okay. I think should we move on to thank Chloe for the great talk. Good job.